What happens when your blockchain-based trust system suddenly needs to handle 10 times the traffic, under strict SLAs and regulatory scrutiny? In this module, we'll treat performance and capacity as first-class design concerns, so your network stays predictable when it matters most. In permission networks, performance is really about trust under mission-critical conditions. Public chains optimize for openness. Anyone can join, hardware varies, and performance is best effort. That's fine for open ecosystems, but not for clearing payments, issuing licenses, or coordinating agencies. Permission networks flip that mandate. You deliberately control who runs nodes and the infrastructure they use, so you can demand predictable latency, guaranteed throughput, and high availability. Here, performance becomes part of the trust contract with every participating organization. Designing blockchain-based trust infrastructure starts with clear definitions of success, not just cool technology. 3 metrics dominate your SLAs. Throughput is how many transactions per second you can reliably commit at peak. Latency is how long a transaction takes from submission to finality, especially at the 99th percentile. And uptime with durability is how often the system is available and whether any data is ever lost. In regulated environments, access speed matters as much as privacy. Before you size or tune any blockchain network, you need to understand its workload. First, what is the mix between writes and reads? Writes are expensive in consensus and storage. Reads are comparatively cheap. Second, how does load vary over time? Daily cycles, batch jobs, and regulatory deadlines. Finally, focus on bursts. Capacity planning is driven by peak load, not averages. Your architecture must survive those spikes without failing. When you evaluate a blockchain as trust infrastructure, 3 performance metrics really matter. Throughput, often measured as transactions per second, tells you how much business the network can actually process, both globally and per channel or shard. Latency is the time from submitting a transaction until it's irreversibly committed. This drives user experience and workflow design. Chain growth is how quickly the ledger's storage footprint expands, which directly affects hardware sizing and long-term operations. Horizontal scaling in permissioned blockchains mostly helps with reads and resilience, not unlimited writes. As you add validator nodes, more organizations can directly verify the ledger and you gain fault tolerance. But every validator has to communicate and vote, so consensus messages grow, and commit latency typically increases. If you spread nodes across regions, you improve survivability against regional outages and align with jurisdictional rules. Yet you're now bound by speed of light round trips between regions. The key idea: beyond a certain point, extra nodes and better hardware deliver diminishing returns for write throughput. You also have to consider protocol limits and alternative scaling patterns. Partitioning is about splitting the blockchain into multiple, semi-independent tracks so they can run in parallel. Instead of a single global bottleneck, each domain, tenant, or workflow gets its own slice of state. Channels or subnets isolate transaction flows, so congestion in one slice doesn't slow others. For regulated environments, this also maps nicely to privacy and jurisdictional boundaries. Done well, partitioning can give you almost linear scalability as you add more partitions. The read-write split is about protecting the most expensive part of your blockchain system, consensus. You keep the consensus layer very lean. It only processes commands that actually change state, and it does so with strong guarantees. Reads are handled elsewhere: replicas, indexed views, or external databases optimized for queries and analytics. By offloading heavy reads, you increase throughput, simplify scaling, and keep consensus focused on what truly matters. Byzantine fault-tolerant consensus is where we hit a hard scaling limit. To agree on each block, every validator has to talk to every other validator, often multiple times. That's where the O of n squared comes from. When you double the validators, you don't just double the messages, you roughly quadruple them. For enterprise or government networks, that means latency and bandwidth demands explode as the validator set grows. So the design pattern is: keep the true validator group small and well-governed, and add non-voting observer or replica nodes for redundancy, analytics, and local access. You trade maximum decentralization for predictable performance and operational simplicity. Once you move from does it work to does it meet the SLA, fine-tuning becomes critical. Here we focus on 3 powerful levers. Block size or batch controls how many transactions are packed together. Larger blocks push throughput up, but each transaction waits longer. Block interval sets how often blocks are produced, which directly affects latency. Endorsement policies define how many and which organizations must sign, trading speed for assurance. You can't just hope a blockchain-based trust layer will meet SLAs. You have to prove it. Validation is about systematically benchmarking the network before production. We care about three big questions. In steady state, can the system comfortably handle realistic, day-to-day load? Under stress, where does it actually break, and how does it fail? And during failover, what happens to performance when validators or nodes disappear unexpectedly? Capacity planning for a permissioned blockchain is a continuous loop, not a one-time sizing exercise. You start by designing around explicit SLAs, throughput targets, latency bounds, and availability requirements that your agencies or enterprises actually care about. Then you benchmark a realistic workload to see how the network behaves under stress. Next, you monitor real traffic and conditions over time, looking for bottlenecks and emerging risks. Based on those observations, you tune configuration, hardware, topology, or even parts of the application stack. Then you repeat the cycle, because business volume, regulations, and participants will keep changing. Here's the executive view to carry forward. First, performance is intentional. You've locked in SLAs, modeled realistic workloads, and scaled the architecture with partitioning and offloading where it matters. Second, you respect the physics of BFT by right-sizing validator sets. Finally, you don't trust assumptions. You validate them with disciplined benchmarking using tools like Caliper. When your ledger becomes the system of record, performance isn't a nice-to-have. It's your credibility. Every timeout, every stalled block is a trust event. As we move forward, think like an architect. How much latency, throughput, and resilience would your stakeholders actually bet their careers on?